Hello everybody, so this is the fifth and last video associated with chapter 5 of the reinforcement learning course. So today we're going to pursue our discussion on off-policy learning in the context of Monte Carlo methods. Okay, so the idea in off-policy methods is that you generate episodes of a Markov decision process with one policy. We denoted it by B, which was referred to as the behavior policy. And then from these episodes, you want to infer the value function of another policy, pi, which is called the target policy. So the idea we pursued to do that is to use importance sampling, where when you average rewards or returns in the various episodes associated with the various states and actions, uh, you had to apply a corrective factor, which was called the importance sampling ratio, which reflected the relative probability of observing some episode between uh, the target policy pi and the behavior policy b. Okay, because when you generate episodes with policy b, some episodes will be more likely than if you considered another policy pi. So you have to reflect this discrepancy by multiplying all returns by corrective factors, and then by averaging all such returns with the corrective factors, then you would be able to obtain estimates of the value function under the suitable policy pi and not under the policy b under which you've generated episodes. So in the previous video, we did that for the state value function. Now here we're going to see that you can do an analogous work for the action value function. Okay, so it's also possible to estimate the Q function here, Q pi SA, or the action value function, through importance sampling. Okay, so it can be shown that to estimate this, this can be written by definition as the expectation of the return, given that you start in state S and you perform action A immediately and then subsequently follow policy pi. But again, if you use importance sampling, it can be shown that this expectation under pi can be written as an expectation under policy B of the return, yes, but now times the importance sampling ratio. Now a quick note, so when we considered the state value function, the importance sampling ratio was rho t to capital T minus 1, but now here we have t plus 1. So why is it the case that for action value functions, the importance sampling ratio starts at t plus 1, whereas for the state value function, the importance sampling ratio starts at time t? The reason is that when we consider the function q, we assume that we fix an action A at time t, so we don't have to consider its relative likelihood under pi or b, because we assume that this action happens with probability 1 at time t. Okay, so you fix that action. So because that's the case, then we shouldn't have to consider the ratio of the probability of that action under pi and under b, because we fix that action when we estimate the function q, which is the action value function. Okay, so here we're going to provide a more detailed explanation in the next slide. So if you're in state S at time t and you do action A at time t also, and then subsequently you follow a policy pi, then you can calculate the probability of observing everything subsequent in the episode, which is the subsequent reward, state, action, reward, state, action, etc. until reward and the terminal state. So here, this probability where, okay, here at the denominator, it's according to policy pi, but the numerator, but at the denominator, it's exactly the same quantity under policy b. So we'll illustrate this for the numerator, but then for the denominator, it's going to be the same. Okay, so if we want to calculate this quantity, then for a fixed state and action at time t, then you can calculate the probability of the next reward and next state according to the transition function here. And then subsequently, once you know these two guys, you can calculate the probability of the next action. So here, this is pi at plus 1 given st plus 1. And then once you know the next action, then you can calculate the probability to reach the subsequent state and reward. Then from the subsequent state and reward, you can calculate the probability of the subsequent action, and etc. Okay, so here, this probability using conditioning can be written as this big expression, which is analogous to what we have here. But now, since we condition on action A at time t, nowhere in this big expression there's the probability of action AT appearing. Okay, so the first action for which we compute the probability, it's when k is equal to t plus 1, it's action AT plus 1. So here the term involving the probability of AT, it's absent here for the action value function. Okay, so again, all the p's cancel out with each other, so what's left in that big product is the product of the probabilities of the various actions in the episode starting at time t plus 1, given the state at the contemporaneous state. And the denominator, it's the same thing for under policy B, where this guy, if we go back previously, this was denoted by row t plus 1, capital T minus 1, instead of starting at t, because this product here starts at t plus 1. Okay, so here this shows that we can pursue exactly the same idea if we want to estimate action value functions using importance sampling. So we can generate many episodes with a policy B, and then consider, so let's say we want to find q pi sa, the action value function in state S and action A. You can look across all the episodes, all the times at which you took action A in state S, look at the associated return at that time, and then for all these returns, instead of simply averaging them to obtain an estimate of the value function, you average them times the importance sampling ratio. Okay, so every time you have a return, you multiply it by the corresponding state importance sampling ratio, which is defined here, and then you average these products through all instances where state S and action A were encountered. And then this is an estimator of the action value function. Okay, so now to conclude this, to pursue on this part, we are now ready to formally provide an algorithm that estimates the state value function of a policy pi, of a fixed policy pi, following another policy B, which is the behavior policy. Okay, so here in this algorithm we're going to present, this is only to estimate the value function. This does not involve refining the policy pi. Okay, we consider a fixed target pi and we want to estimate its value function. Okay, so now a bit of notation. I here will be the index of the episode. So we're going to assume we simulate in total capital I episodes. Then tau is is the set which contains the time of the first visit to state S in episode I. And if state S was never visited in episode I, then this set tau I is null. Okay, this becomes a null set. So here, tau star I S is the set which contains the time of all visits to state S in episode I. Okay, so for example, if state S was visited twice in episode I, then this set here, tau tilde, would contain two values, whereas tau here would only contain the time of the first visit. So here, rho t capital T minus 1 I is the likelihood ratio starting at time t for episode I. GTI is the time t return for episode I. Okay, so here this is clear. This one, it was defined in the previous slides. So this is basically, let's go back a few slides here. This is basically our definition of the importance sampling ratio. And this guy, of course, if you change episode I, the actions and states will change, so the importance sampling ratio will be different across the various episodes, and furthermore across the various time points. Okay, so of course, if you change t to another value, then you'll have a different importance sampling ratio. Okay, so how can we proceed? As we mentioned, we can, to estimate the value function according to policy pi, we can generate many episodes using policy B, the behavior policy, and then we can have the following estimator. So VIS, which is the estimated value of state S after generating I episodes in total, we can express it as the following. Okay, so it's the sum across all episodes of here, the sum across all elements in tau I. So here, this, in fact, it's written like a summation, but it's either two things. Okay, so if state S was never visited in tau I, then this state is null and this summation contains 0 elements, so it's simply 0. Or if state S was indeed encountered in episode I, then this set contains a single value, which is at the time of the first visit. So here, this summation is just a single term, which is the return and associated importance ratio, which were observed the first time, which are associated with the first visit to state S in episode I. Okay, so this is the numerator, and here at the denominator, this is sum across all episodes of the cardinality. So cardinality is just the number of elements in the set of tau IS. Okay, so here again, this set, the cardinality of that set is either 0 or 1. So it's 1 if state S was at least visited once in episode I, or 0 otherwise. Okay, so here, the denominator here, it's just the number of episodes across all of them for which the state S was visited in the episode I. Okay, so it's the number of episodes for which state S was visited. That's the denominator. Okay. So, here, this, just quickly, okay. So here we saw that this is an unbiased estimator of the true value of state I, because the expectation of this guy here, the importance sampling ratio times the return, is indeed the vpi, the state value function of applied to state S under policy pi, which is the one we're trying to estimate. Okay, So this estimator here, where you, as we said, we take all returns associated with first visits to state S in an episode, multiply them by importance sampling ratio, and then average all these quantities. This is the what we call the ordinary importance sampling estimator. Okay, so we might think, okay, we're done. This is great. But an issue with that in practice is that the importance sampling ratio is often very volatile. Okay, so sometimes it will take very, very high values. Sometimes it can take very, very small values. And this is problematic because if the importance sampling ratio is very volatile, although our estimator will be unbiased, it will have a very large variance. Okay, so recall we said that the expected value of the importance sampling ratio is always 1. So this we saw in the previous class, but it can sometimes take values very close from 0 or 0 itself or very large values. So for example, if there's an episode that is 10 times more likely under policy pi than under policy b, then the likelihood ratio will be 10. Okay, and the return obtained for that episode will contribute 10 times more to the estimate than if we estimated the state value under B. Okay, so the weighting factor for the which are the importance sampling ratio for all returns can be very volatile. So either very large or small, and this is problematic from a variance perspective because if the importance ratio is very, very high for some values, for some paths, then the return will have a weight that is much too high in the estimator. So if the return departs very highly from its expected value, you'll make a high estimation error, and then therefore your variance of the importance sampling estimator will be very large. Okay, so is there a way to go around this problem? The answer is yes, and in practice there's what we call a weighted importance sampling estimator, which can replace the ordinary sampling estimator. Okay, so here this estimator, the weighted importance sampling estimator, it's an alternative which allows to mitigate the problem of very high variance for the ordinary sampling estimator. So the weighted importance sampling estimator looks pretty much the same, but here at so the numerator is exactly identical, but the denominator is different. And the denominator here, instead of counting the number of episodes for which state S was visited at least once, what we do instead is for each of such first visits, we sum the associated importance sampling ratios. Okay, so the cardinality of tau is replaced by this summation here, which is the importance sampling ratio associated with the first visit in all the respective episodes, and 0 if for some episode that state S was not visited. Okay, so first, what are the properties of this estimator? Well, first, it can be shown that unfortunately this estimator is biased. Okay, so can we see that? The answer is yes. So let's take an extreme example where the state S was visited a single time across all episodes. So for episode I, let's assume that state S was visited at time t, and then state S was not visited in all other episodes. So in that case, if we go back to the previous summation, these summations across the various I, well, there's a single term which is non-zero because for a single episode, the state S was visited. So this becomes simply the numerator here divided by one term in the denominator. So it's just importance sampling ratio times the return divided by the importance sampling ratio for episode I, where state S was visited at time t. Importance ratios, they simplify, and then this only becomes the single return associated with the single visit to state S. So if we calculate the expectation of this guy under the policy for which we generate episodes, then the expected value of this is VBS instead of V pi S. So we're trying to estimate V pi S, but since episodes are generated with policy B, then this estimator becomes VBS instead. Okay, so we see that this estimator is biased in general because when we consider its expected value, it might differ from the true V pi S. However, the estimator is consistent. So although it is biased, when the number of episodes converges to infinity, then the estimator is consistent in the sense that the bias will converge to zero, but not only the bias, the estimator will converge to the true value. Okay, so let's see that. We'll give a short proof for that, the consistency of the weighted importance sampling estimator. So let's define the following. So AITS is the following events, which is that the first visit to state S in episode I is at time t. Okay. Then Then we have the following. So here our estimator, weighted importance sampling estimator, this is exactly this equation. So this is the definition, but now we divide it by 1 over I at the numerator and at the denominator. Okay, so we're allowed to multiply and divide by the same constant. And then as I goes to infinity, so as the number of episodes goes to infinity, then this will converge to its expectation, and its expectation, the expectation for a given path of the importance sampling times the return, it can be obtained by conditioning on the time at which the visit to state S was performed. Okay, so here if we consider conditions, on the time at which the first visit to state S was performed, we can have the following. So we can sum. So here this 1 over I, sum over I, it converges to an expectation because it's some sample average across independent paths. So we can use the law of large numbers so that this summation transforms into an expectation. And here, as we said, so if we consider here the importance sampling ratio and the return for the first visit to state S, we can condition on all possible values of the first visit to state S. So it's the expectation of this product given that the first visit to state S is at time t times the respective probability. Okay, so here we can do that at the numerator and at the denominator, but here at the denominator the return is not there anymore, so this is why G is not present here. Okay, and then here this quantity above here, this is V pi S. Okay, so given that, so this event implies that at time t you're in state S, so this is the expected return times the importance sampling ratio. So expected return means this is the value function, but since we use an importance sampling ratio, the expectation under B becomes an expectation under policy pi. So this is a V pi S. And here below we said that the expected value of the importance sampling ratio for any t is always equal to 1. So this becomes 1 here. So here these are constants. They can go out of the summation, and then at the numerator and the denominator we end up summing these probabilities under policy B of these events, which cancel out, and this becomes equal to V pi s. Okay, so this shows that as the number of episodes converges to infinity, our weighted importance sampling will converge to the true value function. Okay, so this is a proof of consistency. So although this estimator is biased, it will converge to the correct value. Okay. So we said that the ordinary importance sampling method did sometimes provide very volatile estimates. Well, it can be shown with specific examples. So here I haven't provided such examples, but in the textbook they do illustrate a specific case where this happens. It can be shown that sometimes the variance of our ordinary ordinary importance sampling has unbounded variance. Okay, so when you have unbounded variance, typically the convergence is very slow. Okay, so you through the large law of large numbers, you will still have convergence, but you cannot invoke the central limit theorem here due to infinite variance. So because of that, then it can be the case that the convergence becomes much slower in that case. Conversely, it can be shown that weighted importance sampling are much less volatile. So why is this the case? So here, let's go back one slide here. So this is if we forget about the 1 over i's, this is the definition of the weighted importance sampling ratio. So here at the denominator, we can enter that in this denominator inside the two summations here. So we can have summation of this row, the importance sampling ratio, divided by this summation. Okay, so in that case, this becomes summation of row divided by the denominator. So then this becomes the weight associated with return I in our weighted importance sampling estimator. And this weight here, it's always smaller or equal to 1. Okay, so in the previous case, the weights were not bounded. In ordinary least squares, the weights for the various returns in our estimators, they were not bounded, whereas for weighted importance sampling, the weights are bounded. So this is why this method, weighted importance sampling, is typically favored in practice. It's because the weights are bounded, they're much less volatile, so the importance sampling estimator is much less volatile, also more precise. Okay, so we've exhibited an approach based on the first visit to estimate V pi, the state value function under policy pi, based on an importance sampling approach. We could also consider every visit's approach. So instead of considering the first visit to state S in a path, we could consider all visits to state S in the path, multiply their associated returns with importance sampling ratios, average them, so that you can estimate V pi S. Okay, so here we'll omit the fine details, but the textbook states that the every visit methods for both ordinary and weighted importance sampling are both biased. Okay, so we said that the first visit method for ordinary importance sampling was unbiased, but here this is not. If we consider the every visit version of the algorithm, this is not the case. So the bias does exist, but once again, the bias can be shown to fall asymptotically to 0 as the number of samples, and here by samples we mean the number of episodes, increases. Okay, so does that mean this bias make these every visit methods unuseful? The answer is no, and even in practice, they are often preferred because first, when you have an every visit method, you don't need to keep track of which states or state action pairs are visited in each episode. You just consider all visits to state S regardless if state S was visited before or not. Okay, so it's easier to compute and practice because in a given episode you don't need to track all previous states that were visited. Um, and furthermore, we're gonna see, and this is only later on, that the every visit methods they're much easier to extend to approximations. Okay, so here we won't tell more about that. We'll uh, go back to that subsequently. Okay, so here uh, we're going to provide an example very shortly of an every visit Monte Carlo method for off policy evaluation based on weighted importance sampling. Okay, so this is going to be done shortly. Okay, so recall that from chapter 2 or even in this chapter we had a recursive formula for the estimate of our value function. Okay, so in practice, if you have finite memory, you don't necessarily want to keep track of all the states that were visited in all episodes because this might require way too much memory. So in that case, you need a recursive formula where the only thing you need to keep track of is the previous estimate of your value function, maybe some other quantity, counting the number of times you went into a given state or something like that. And then based on these information, you can update your value function. Okay, so proceeding like this with a recursive algorithm prevents the need to keep track of all states and actions which were visited in the past, which is in practice sometimes infeasible because it will require too much memory. Okay, so now we're going to study this recursive relationship. We're going to introduce a bit of notation. So here VNS will denote the estimator of the state value function in state S, so the value of state S, after having sampled n minus 1 returns starting in that state S. Okay, so here VNS is the estimate of V pi S after n minus 1 episodes were generated where there was a visit to state S. Here GKS, it's denoted as the kth returns sampled in the episodes which started in state S, and here rho KS is the importance sampling ratio for that kth return starting in state S that you observe in your data. Okay, so here we can notice that the importance sampling ratio for both ordinary importance sampling and weighted importance sampling can have the following formulation. So the estimate of the value function in state S can be written as the sum across all previous visits to state S of a weight quantity times a return quantity divided by the sum of such weights. Okay, so for importance sampling, so the weights W here, you can set them equal to 1, and then the return here, G tilde, it's the true return you obtain from your kth visit to state S times the associated importance sampling ratio. Okay, so when you multiply returns by importance sampling ratio, this is the traditional importance sampling estimator. Conversely, for the weighted importance sampling, the weight is the importance sampling ratio, and here the G tilde return is the true return itself. Okay, so when you consider weighted importance sampling, the numerator is the sum of returns times importance sampling ratio, but then the denominator, instead of being the sum of once, which counts the number of episodes in which state S was encountered, then for weighted importance sampling, you just sum the weights, which was the sum of all associated importance sampling ratios. Okay, so this is for estimates of Vs, the value of state S, but you could derive analogous formulas for the Q function, for action value function estimates. Okay, so we won't provide the details, but it's pretty much the same idea. Okay, so note that here, let's define C and S being the sum of all across all n first visits to state S of the weights associated in each visit. Okay, so the weights, recall that for ordinary sampling ratios, this is simply weight is equal to 1, so this summation is simply equal to n, whereas for importance sampling ratio, this W is the importance sampling ratio in the kth visit to state S across episodes. So here, when you sum these, this is just the sum of all previous importance sampling ratios. Then it can be shown that we can apply the following recursive formula to evaluate or estimate the value of state S. Okay, so the estimate after the first n visits to state S is the prior estimate after n minus 1 visits plus the weight associated with the nth visit divided by Cn. So Cn, recall, is the sum of all weights for all previous visits of the return minus the previous estimate. Okay, so this expression, it's a bit analogous to what we had earlier. So next estimate is previous estimate plus some form of learning rate or pace of learning of the target, the guy for which we want to estimate the expected value, minus the current estimate. Okay, and here this relationship holds if we set that V1S is equal to 0 or any arbitrary number. So this is just the initial value of your estimate for all states. C0S defined as 0. So this summation here, when it has 0 term, it must be equal to 0. And then clearly from this relationship, it's easy to see that Cn plus 1S, so the sum of all weights in the first n episodes is the sum for all weights in the first n minus 1 episodes plus the n plus 1th weight. Okay, so now we're gonna give the proof for this following statement. It's not a very complicated proof. So here, so the first line here, recall that let's write that. We had the formula which said that Vn plus 1 S was equal to sum W, I'll just here until n divided by the sum until n, this is an n of the W. Okay, I'll omit subscript just to make it simpler. So here we can, and this denominator here, this guy was denoted by Cn. Okay, let's Cn like this. Okay, so here we can take the Cn and put it on the other side. So this says that Cn Vn plus 1S is equal to the sum of weights times the G-tailed, which are either the returns or modified returns, depending on if you're in importance sampling or weighted importance sampling. And then this summation here, so maybe I'll erase this. This summation, you can break it into two, so you can consider the first n minus 1 terms and then the nth term. And then to go from here to here, we have to notice that this is exactly the same equality if we replace n by n minus 1. Okay, so here if we replace n by n minus 1, this quantity becomes Vn, and here this is a sum until n minus 1. So this is why we have that this guy, which is c minus 1s Vns. So this guy is like this guy, but with n minus 1 replacing n. So this guy should be equal to this guy, but where n is replaced by n minus 1, which is exactly this term. Okay, so here we said that Cn, so recall Cn, it's the sum of the w's until index n. So here Cn, Cn minus 1, of course, it's Cn minus the last term here. Okay, so if you take Wn, so here Cn minus Wn, this is the sum of W until n minus 1. W here. Okay, so this is how you get to this term here. And then what you do after, this is just first you take this expression here, you divide by Cn on both sides, so you can do that. Then this first Vn goes to here, and then you can factor out the W, whoops, the Wns, and then by factoring these W and S, you obtain this guy, and this is exactly the formula you've obtained. Okay, so this shows that both the ordinary sampling estimator or the weighted importance sampling estimator, they can be computed recursively through some simple recursive formula. Okay, so what we did previously, we provided algorithms for the policy evaluation problem, which is for a fixed policy pi, you want to estimate its value function. Okay, so in previous algorithms, we did not attempt refining pi so as to try to converge to the optimal policy. We considered a fixed pi and estimated its value function. Now we're going to provide an example of a control algorithm, which is an algorithm which does indeed refine the policy to attempt converging to the optimal one. So the value function estimate in that case will not be an estimate of v pi, it will be an estimate of the optimal value function because we want to have the policy converge to that optimal value function. Okay, so the algorithm we're going to provide is an off-policy Monte-Carlo approach. So again, we generate episodes from one policy and try to estimate another policy. The approach we're going to use, well, first, instead of calculating directly V star, we're going to calculate Q star because when we do control, we must refine the policy, so there must be some comparison of the values of the various actions to optimize policy. So instead, we require to compare the value of various actions. So to estimate V pi, we will estimate, V star, we will estimate instead Q star to obtain V star as a side product. Okay, so the approach we're going to see also still relies on the generalized policy improvement framework, where you have some policy evaluation where you refine your value function to better match your current estimate of the policy, and then policy improvement step where for the current estimate of the value function you make the policy greedy with respect to that value function so as to try to refine your policy, which is inspired from the policy improvement theorem. The algorithm we are going to present uses weighted importance sampling instead of the regular importance sampling. And furthermore, the behavior policy which we use, in practice you can use many policies, but this algorithm that we're going to present uses epsilon soft policies. Okay, so these policies, they allow for continuous exploration, and they guarantee that the coverage assumption discussed earlier is satisfied. So recall the coverage assumption says that all actions that are deemed possible in policy pi must also be possible under policy b. Okay, so how does this algorithm work in practice? So I've pasted a pseudo code from the textbook, and this is how it works. Okay, so first, this is what you do all the time. So here, QSA. So for all states S and actions A, your initial estimate of the of Q star, the action value function, it's arbitrary. So you start with arbitrary estimates for that value function, and you're going to refine them. CSA. So recall that C is the sum of weights W for each visit to state SA. Okay, so the sum of weights, at the beginning, you have never encountered state SA, so when you sum weights, you sum nothing, so you can assign the initial value of 0 to that value. And then here, your initial policy, or your initial estimate of the optimal policy is to take in each state S the greedy action. Okay, so policy pi, the target policy, is initially estimated as for each state the action which maximizes your current estimate of the Q function. Okay, so at the beginning this is very bad because we arbitrarily initialize the function Q, so the policy might be very poor at the beginning, but doesn't matter, we're going to refine it. Then once you do that, you can loop forever. Of course, in practice it's not forever, but it should be for a long time if you want sufficiently precise results. Then forever, or for a long period of time, where you're going to do the following. Okay, so first you're going to select policy B as any soft policy. So here, this is inside the loop, but in practice, you're not obliged to change your behavior policy in every iteration of the loop. This could be outside the loop. Okay, but you can still put it in the loop, and for every time you make a new episode, you might want to change your behavior policy for some reason. Then from this behavior policy, you generate an episode, state, action, reward, etc., until the final reward. And then you do the following. So here you assign the value 0 to G. So G will be the placeholder for the return that we're going to consider. And you assign a value of 1 to W. So W will be the weight W that we've defined earlier. Okay, we're going to assign it a value of 1. We're going to see why. Then what's going to happen is that we're going to, based on this episode, every time we observe a new reward, we're going to update the action value function estimate based on this new information, this new reward. Okay, so here, what you could do, you could start at the beginning, and every time you observe a return, okay, because when you observe rewards, you can calculate present value of discounted rewards or sum of discounted rewards, so you can obtain returns G in all steps. So you could start from the beginning, but the textbook proposes to start from the end of the episode to update the values of this state. Okay, so why is that the case? It's because from a coding perspective, it's very natural. We're going to see why. Okay, so for this episode, the textbook proposed to loop through the various time steps, starting at the end until you reach the beginning. So you start at time t minus 1, then t minus 2, then until 0. And then for each of these steps, you do the following. So you replace your current value of the return by the gamma times the previous value plus r. So the reason for that equation is the following. So recall that gt is equal to r rt plus 1 plus gamma gt plus 1. So if you do that, so let's assume you have the return of the next time step. If you add the current reward and multiply the next return by gamma, then you obtain the return from the previous time step. Okay, so this is why this happens. Okay, here then this step, you so assuming at time t you're in state st and at, then you're going to modify the value of the factor c we've defined earlier by taking its previous value and adding w. Okay, so w will be the weight. So recall this comes from which equation? It was that, or maybe um, okay, so why is that the case? Let's go back here. Just give me 1 second. This is the value. Yes, okay, so here, if we go back here, C was defined as the sum of all weights for every previous visit to your state S across all the visits you've considered. Okay, so here, because you're considering a new visit to the state action pair S, ST, AT, then you should increment C, which is the sum of all previous weights to uh, during visits of this state action pair. So you should take the previous value and add the weight to it. Okay, because we had the following relationship. So C n was the sum of until index n of wj. Okay, something like that. Okay, so this formula here is why we have this equation. And then once we have that, then we can apply our recursive formula to update the value of our estimator for the value function in state st and action at. Okay, so we had a formula where the next estimate of your value function is your previous estimate plus the current weight w times c. Okay, so here this is the C, recall this is the sum of all W's for every previous visits of S and A that you've considered times what we call the target. So the return here minus your here this is the previous estimate of the Q function. Okay, so why do we consider this? Let's go back a few slides. This is exactly this formula that we've considered. And here, when we use weighted importance sampling, G tilde was exactly the return. Okay, so this G tilde becomes the return itself. So we have something like next estimate of the value function is the previous estimate plus W over C. So the current weight times the sum of all previous weights times the return minus the previous estimate. Okay, so here it's exactly the same formula, but we do it for action value functions Q instead of state value functions V. Okay, and then the following steps will require a bit of explanation. So then what you do is the following. So you're going to check according to your new estimate of the value function, you're going to check what is your optimal action or your greedy action, I would say, in state ST. And to do that, you check across all actions A, the value of the various actions according to your current estimate Q in state S. And here the action which gives you the maximal value, maximal estimated value, this is the greedy action, pi of st. Okay, because we say that the current estimate of the optimal policy is the policy which is greedy with respect to your current estimate of the value function. Okay, so if your current action is different than the greedy action, then you break this loop, loop where you go over all time step, you break it, and then you proceed to the next episode. Conversely, here, if the action you took at time t is the greedy action, which is the estimated optimal action, then you're going to update w to w times 1 over BATS given AT. Okay, so given the probability of selecting action A and ST under your behavior policy. Okay, so this seems very mysterious, but here, okay, let's explain why. Okay, so here at time t, the importance sampling ratio is of the form product from t plus 1 to capital T of, we had something like pi a. Okay, so j goes from t plus 1. So j, this is j goes from t plus 1 by aj given as j divided by, the b aj. Okay, but now we are in a control, a controlled setting where the policy pi is our target policy that we want to optimize, and thus the current estimate of the optimal policy is a deterministic policy which is greedy with respect to Q. Okay, so this policy pi, because it's the greedy estimate, it either assigns a probability 1 to the greedy action pi of st, or a probability 0 to all other actions. So then we observe the following. So here, this implies that rho t is equal to rho t plus 1 times pi at plus 1. Okay, here I should consider a condition on S, but just to make the notation more concise, I won't write the conditioning here. Okay, so here, here. Okay, so we can see here that recall that in the weighted importance sampling, the weight W is the importance sampling ratio. And here, we see what's happening here is that the previous importance sampling ratio, one step prior, is, in step T, is the importance sampling ratio at the next time step times pi I divided by B. Okay, so here, this B, we see where it is. And here, this is why we have a 1 here. It's because if action A was the greedy action, then, So sorry, there's a mismatch in the index. So this is AT, this is T plus 1. I'm sorry about that, but this algorithm is correct. Okay, so please, when you revise a note, make sure uh, please correct my mistakes with respect to the index. Okay, so it's probably rho T minus 1 in comparison to rho T. Okay, I'm sorry about that. But here, this quantity here, it's either 1 if the action is the greedy one. So if the action is the greedy one, then this guy becomes 1. So this is why there's a 1 here. And if it's not the greedy action, so if the action is different from the greedy action, then what happens is this term here becomes 0. So the importance sampling becomes 0 for all values of t prior to this. Okay, so if this is 0, then rho t will be 0, but rho t minus 1 will also be 0 because rho t minus 1 is rho t times something. So, and then rho t minus 1, rho t minus 2, rho t minus 3, rho t minus 4, all associated importance sampling ratios will become 0. So, for all previous steps, when you will apply this update formula, this W will be 0, so this term will disappear and all estimates will become identical to their previous one. So this is why if this guy becomes 0, then you can break that loop because you will stop refining your estimates for any subsequent time step or prior because you go back in time. Okay, so this is why these steps, they look a bit mysterious, but this is what explains first the 1 here. It's because this guy is either 0 or 1 because pi is a greedy deterministic policy. And this is why you get, when you don't take the greedy action, you break the loop because all importance sampling ratios, they become 0. So you stop refining your estimates for the current episode. Okay, mystery solved. Please, I understand this might be a bit hard to digest the first time you hear about this, so please take some time to digest this as if this is a bit mysterious. Okay, please take the time to reflect on this because it's important. Okay, so some quick notes. Okay, so here, this slide, I won't repeat it because it's exactly what I've explained in the previous slide with the business of pi being replaced by either 1 or 0. Okay, so for this slide, I'll skip it because it's exactly repeating what I just said. But if what I just said was not clear to you, feel free to read that slide because it's useful for explanations. Okay. So the textbook states that under this algorithm which we provided, then the target policy estimate, so pi, which is the policy that is being refined through time, so here I use pi, but in theory it should be pi n because it's a sequence of estimated policy, then this sequence will converge to the optimal one according to the textbook. So I admit I haven't read the proof for this, so I'll just assume that the textbook is right about this. Okay, so according to the textbook, the algorithm we just presented should converge to the true policy when the number of episodes converges to infinity. Okay, so it converges to the true policy, but one question you might ask yourself is how fast will this converge? And what you can it's possible to see that the convergence of the latter algorithm might be very slow if you explore a lot. And why is that the case? It's because, as we mentioned, every time you select a non-greedy action, then the weights of the importance sampling ratios, which are the weights, they become automatically zero, and then you stop updating your um, your values of the action value function for all previous time steps in the episode. Okay, so maybe you start by the end. So for step capital T, maybe you update update your values, but then at some point T, the importance sampling ratio becomes zero, and for all prior time steps, you also have importance sampling of zero, and thus you do no update of your values. So as you don't update your values, well, you've just simulated a whole episode with where much of it is discarded, and we only learn from the tail of the episode, which is the last reward states in action until you reach one point where you select a non-greedy action. Okay, so if there's a lot of non-greedy action exploration, this algorithm will be very slow because the tails of episode will be short. Okay, because every time you face a greedy action, you stop updating. A non-greedy action, you stop updating your values. So in that case, the temporal difference methods presented in the next chapter work well. Okay, so we've presented kind of intuitive, uh, maybe not all of them, but many of them of the algorithms in this chapter were quite intuitive, I believe, but in practice, there are some drawbacks associated to it, which is that the off-policy methods we've illustrated, they are slow to converge, although they converge to the true value. The on-policy methods, conversely, they could converge faster. Okay, so for the algorithm we've presented, we had no proof of convergence, but they could converge faster, but they couldn't converge to the optimal policy. They could only converge to the optimal policy that explores. Okay, so for example, optimal epsilon greedy policy, which is not the exact optimal policy. Okay, so methods we saw in this chapter were great, but now in the next chapter, we're going to see alternative approaches which can make convergence faster and be more convenient in practice. So, which might allow you to accelerate learning in practice. Okay. So, one quick you might say is that in the previous algorithm, typically as time goes by, the policy is being refined and changed through time. Okay, so as you change your policy, the distribution of your episode changes so that the distribution of the various returns and importance sampling ratios for the various visits to a given state action pair SA, they're neither independent because episodes depend on each other through the policy that is being refined, and they're not identically distributed because the policy changes through time. However, the textbook, as we mentioned, states that you can still have convergence in that case, and the reason for it is that as time goes by, the initial the returns generated by the initial suboptimal policy, they will have less and less weight through time. So as time goes by, you average more and more returns. So the very bad returns you've obtained with a very bad initial estimate of the optimal policy, their weight will gradually vanish through time, and thus these bad returns will become less relevant and have less impact as time goes by. Okay, so as time goes by, when you approach the optimal policy, the return should look more and more IID in that case, which is why you could attain convergence. Okay, so this is the end of the chapter. So I'll see you for chapter 6, where as we mentioned, we're gonna present alternative methods which can alleviate the drawbacks presented associated with the Monte Carlo methods of this chapter. All right, so have a nice day.